Hello, everybody, and welcome to this week's Hubble Hangout. My name is Tony Darnell, and you have found yourself in one of the few places, if not the only place, where you can get direct access to the latest science and discoveries from the Hubble Space Telescope, along with an opportunity to directly interact with the astronomers who use Hubble every day to try and understand the universe and our place in it. So this week, we'll be talking with astronomers from the Space Telescope Science Institute, whose latest research suggests that most of the Earth-like planets in the universe have yet to be born. I mean, that right there just blew me. That caught my attention right away. We'll talk about that and the implications for this for exoplanet research and what it might say about Fermi's famous question, where is everybody? And we'll get to them in just a minute, but before I get started, let me introduce my colleagues, Dr. Carol Christian. She's the HST Outreach Scientist. Hi, Carol, and welcome. It's good to see you again.
Hello.
Missed you last week.
You. Yeah.
You were traveling. That's right.
I was in Jerusalem. That was fun. Anyway,
So this year in Jerusalem. Okay. Also with me, joining me is Scott Lewis. He's monitoring our internet channels and also helping with the discussion. Hi, Scott. It's good to see you again.
Yes, good to see you too, Tony.
Cool. All right. Well, before we get to our hangout and I introduce my guests, I want to do one announcement that I found out over the past few days. NASA's New Horizons spacecraft. I'm sure you guys remember that. Flew by Pluto last July and looked at things and sort of changed our view of that outstanding system of bodies out in the outer solar system. And there's a next stage to the mission, which I think is yet to be funded. I don't think they've gotten funded to complete this part yet, but they need to start thinking about it now. And I was reading Emily Lakdawala's blog last week where she was talking about that they finally have a second target for New Horizons to fly by. Now, I put the link to all of this in the description box, so you can read more about it there. But it turns out that Hubble actually gave New Horizons some potential candidate Kuiper Belt objects to go to, and they are very imaginatively named PT1, 2, and 3. PT for potential target. Now, I think the favorite, according to what Emily has written and what I've read on the Twitter feed from New Horizons, is that PT1 is going to be the most likely one they go to. And so, but they have to kind of get ready now, right? Because, you know, physics. They have to fire the rockets and get the spacecraft positioned such that it can make the flyby in a reasonable amount of time. So they're working on that now. And from what I've seen on the Twitter feed, is that the burn is going to be, what did they say here? It was like it's going to take 4 engine burns over 2 weeks, which totals about 57 meters per second. So that was what their tweet said earlier today. And so they're getting ready for all of that now. And as I said, Hubble had a role in this. We helped them identify some potential targets, 3 potential candidates. If you want to learn more about them, you can go to the link to the planetary.org blog that Emily wrote last week. So just wanted to say that. Also, Astronomy Night happened last week, or Monday. Did anybody happen to see what was going on with that? No? I didn't get to go. We didn't get to go. So,
I just got up to San Francisco. So
I know. I saw your tweets. There. I saw you doing a road trip on the way to San Francisco. So.
Well, anyway, apparently, you know, there was the usual got to get your telescope in, security, all that kind of stuff. But they said it was a very successful night. This year, I don't think the president wandered around so much. He came out and made a speech, yay verily, and then people looked at the moon this year instead of a binary star. Apparently, for some reason, they chose a binary star last year, which I have no idea why people would want to look at that. But anyway, they looked at the moon; they were much happier.
I didn't even think about it. Cool. I'll bet more than one Secret Service agent had a bee in their bonnet over trying to get telescopes on the south lawn of the White House.
Oh yeah, so apparently last year they had to send them in like a day in advance and all that, and this time they loaded all their stuff in the NASA truck and they went over. It was still, you know, a hoo-ha, but they got stuff in there.
Yeah, good. Well, NASA Horizons got a shout out from the president, and a lot of people excited about the work they're doing. So the story is not over with New Horizons, folks. It's hopefully, I don't know when we're going to get word on the funding for the next stage of that project, but certainly data are still coming down, and they're still analyzing it now. We're hearing new things about Pluto. Almost every, exactly.
Yeah, very nice data, and we did help them out by scheduling some observations to see if we could find one of these Kuiper Belt objects for them. And so we accumulated some data for them, and they analyzed it, and they found, as you said, 3 objects, and they picked one. So.
Yeah, and Emily's got a real nice chart on her blog post about the characteristics of each one of the potential targets, how big they are, and all of that, and when it might encounter it. The first one, PT1, is in January 2019, so we got some time before it gets there. But like I said, they have to plan ahead and get the thing pointed, or at least on the right trajectory now, so that when it makes the flyby.
And just in general, I mean, Emily's blog is fantastic. So
Agreed.
Emily Lakdawala, I don't know how she gets out as much work that she does all the time, and I've worked beside her, and she's just amazing. So follow her blog, and her Twitter account is fantastic too.
Yeah, she's a huge source of information for me on Twitter as well. I agree. Yeah. Thanks, Scott. That's good. That's a good point. Okay, so let's get to this week's hangout. Astronomers at the Space Telescope Science Institute. Turns out we do more than just look at Hubble data. There's also theoreticians in the house. Now, I don't know if either of these guys would consider themselves theoreticians exclusively, but we'll talk, and I'll ask them about this in just a minute. But joining me is Dr. Peter Beiruzzi. He's an astronomer and postdoc at the Space Telescope Science Institute. He's joining us all the way from Japan, and so he is woke. So he says it's 4 in the morning there. I want to thank you, Peter. Welcome to our hangout.
Thank you. It's great to be here.
Yes, and because of the time delay or the time difference, we'll be getting audio from him throughout the hangout. So, but at least we have him, and that's great news. He's the lead author of the paper that appeared on the October 20th monthly notices of the Royal Astronomical Society, and also on that paper is Dr. Molly Peoples. She's been in our hangouts before. Hi, Molly. It's good to see you again.
Hey, Tony.
Now you're actually at the institute, so
I am at the institute.
Yeah, and so she joins us. She was also on the paper. Let me get this is Exoplanet Week. I know this because the hashtag is all over Twitter, right? This is
we're trending.
That must be true. Yeah, absolutely.
So it's on Twitter, so it's got to be true. And NASA Goddard and all these, there was a Ask Me Anything on Reddit about exoplanets that Goddard held, and it happened. It was about 2 o'clock, so it's over now. But Exoplanet Week, and so I'm excited because we happen to have exoplanet topics here. It turns out that these guys have done a theoretical study, and we'll talk about what the study is and how they did it, that is showing, or it seems to be pointing out, that most of the world's exoplanets out there that are Earth-like haven't even been born yet. And I want to talk about, to me, that's a pretty astonishing thing, because the universe is 13 billion years old, or a little over, and that's a pretty big statement. So, Peter, can you give us some summary of what you were doing and why you were doing it?
Before we get into our discussion,
oh, thank you, Scott. I knew I'd forget it.
I knew you'd forget it too. It's all right.
That's why we got that.
Exactly.
Please tell these kind of people how they may interact with us.
Yes, so those of you that are watching right now, you can interact with us in various ways. The easiest way for us to interact back with you is using the Q&A app. So you're watching this as a YouTube video. On the bottom left side, there'll be some text saying that we're answering questions, which we are. I see at least some comments going on right now where everyone is saying hello.
Hello, Hubblers.
Ian Harris says, greetings, Earthlings, from the Netherlands. So hello. So you can ask questions there. You can actually upvote other questions. So if there's a question that somebody asked and you want to know the answer to, you can upvote them, and we will see that. And then when we reply, we'll select it, and it'll show that we're answering that question. The other really good way for interacting with us, too, is on Twitter. So I'll be live tweeting from the Hubble Telescope account and using the hashtag Hubble Hangout. So if you have a question or comment for any of us here regarding today's topics, please use that hashtag and we'll reply. I'll also be looking at the event page and on YouTube as well, just with the general comment system. But the Twitter and the Q&A app are the best ways for interacting.
Agreed. And I want to also welcome everybody from the Periscope that we did at 2 o'clock earlier today. If you're watching, thank you and welcome. So that's it. All right, so Peter, tell us a little bit about the work you're doing. You and Molly have been doing with this theoretical study, and what you were. I'd like to know why you were doing it as well as what you were doing.
Sure. Well, so Molly and I were interested in the formation history of planets all over the entire universe. So a lot of the exoplanet science, and it's amazing science, has been done in our own galaxy, the Milky Way, so looking for planets around other nearby stars. We are interested in the planet formation history of not just our own galaxy, but all the galaxies in the universe. And so that's one of the reasons why it's a theoretical study, is that we have no telescopes currently which can even hope to see planets and stars in other galaxies.
That's a good point. So telescopes like Kepler and the space telescopes, and what we do know about exoplanets have been pretty much statements about what planets are in the Milky Way, right?
Yeah, and I guess very nearby stars.
Mm-hmm.
And so we were interested in the Earth-like and giant planet formation histories, but for this hangout, we'd like to focus on Earth-like history of planet formation in the universe as well as its future. So, Scott, if you could pull up the first slide, please. I'd like to talk about what we mean by Earth-like planet. So, all it is astronomers need some definition when looking at other planets. What's in the range of Earth-like, what's not. And so we have a fairly loose definition of Earth-like in the sense that if the planet had an Earth-like atmosphere, it could support liquid water on its surface. And operationally, what that means is that the planet should have a radius within a factor of 3 of the Earth's radius, so a third of the Earth's radius to 3 times the Earth's radius. And its orbital period, that is its year, length of its year around its host star, should be within a factor of 3 of 1 Earth year. So in the solar system,
are these kind of arbitrary numbers? I mean, a factor of 3 within 3 Earth radii, 3 times the orbit of the sun around the Earth.
It's somewhat arbitrary because different groups use different numbers. But the uniting underlying principle is that there should be liquid water if the planet had an Earth-like atmosphere.
That's the key, right? The liquid water part.
And so that's the key, right? Because under that definition of radius of the planet as well as its length of its year. Actually, in the solar system, Venus and Mars would also qualify. Obviously, they don't have an Earth-like atmosphere, and they don't really have liquid water on their surfaces, but we're counting those as Earth-like planets for the purposes of this calculation. Okay.
Oh, okay, that's good to know. So even Venus would qualify here.
Even Venus would qualify. And so that goes into, later on we'll talk about these civilizations, and so of course it's very likely for a civilization to arise on Venus with the temperatures it has. But anyhow, that'll be something we'll talk about a bit later. Okay, that's just to say, what do we mean by Earth-like planets? Okay, so then if you go to the next slide, here's our method. It's very simple. So Hubble can see other galaxies, of course, all the way back to almost the Big Bang. And from the colors of a galaxy, we can infer the star formation rate, that is, how many new stars are being created per year in the galaxy. So for a galaxy outside our own, we can just look at a picture of it and guess how many new stars is forming per year. And then we multiply that by the number of planets that form per star. And so that information is obtained from Kepler observations. And
so wait, that middle bit, there's a ratio, right, of Earth divided by the number of planets per star. And I think from Kepler, isn't it like 1.6 planets for every star, something like that?
Right. So that's total number of planets. And since we're interested specifically in Earth-like planets, right?
So it's going to be some fraction, some number less than 1, presumably.
Some number less than 1, actually.
Right. Okay. So
because I guess some stars do have multiple Earth-like planets like the Sun, but then some stars have none. And so it turns out that on average for stars like the Sun, you have, that is K to F5 class specifically stars, you have about 10% on average that have an Earth-like planet.
Oh, so that's another bit then, right? Not
exactly.
Just so you
I
had
was going to ask about the type of star because it was implicit in what you were saying that there's certain kind of stars you're considering. So maybe you can explain the types of stars. I mean, they're roughly sun-like, but explain, your criteria for the stars.
Right. So the current thinking is that if the mass of the star is too small, so
like a brown dwarf or something like
less
that.
Than about, well, even even less than about 0.6 solar masses. Then there are two issues, one of which is that the planet has to be so close to the star that it gets tidally locked. So much like the moon is tidally locked to the Earth, so we only see one face of it. The planet would have one face always directed toward the star and one face always directed away. So one face would be burning hot, sort of like Mercury, and one face would be deadly cold. And so it would be hard to imagine that life would easily form on such a planet. And the other problem with a very low mass star is that they're often variable. And so you'd have huge ranges in temperature, not just from which side of the planet you're on, but just even in one spot on the planet, you'd have huge variations in temperature from just the star itself getting brighter and dimmer as a function of time. And so that's also potentially inhospitable for life. And once you get to very massive stars, then you have a lot of UV radiation and other, I guess, nasty things that would potentially sterilize any organic compounds that would make up life. And so there you'd also have a difficult time imagining that life could exist on planets around such stars. So that's why there's a fairly narrow range of 0.6 solar masses to 1.4 solar masses where we think there could be life on planets around such stars.
So that middle term there, there's a lot in that.
There's a lot in that. That's right.
So you've got a lot of factors playing into it, not just planets per star over the number of Earth-like planets. There's a lot of other things you're considering that are implicit in this as far as the rotation rates, the being tidally locked. I didn't even think about that. And then how much gold they have in the bank matters. Oh, sorry.
That's right.
Sorry. Go ahead.
You can't fund a planet from nothing, right? So,
That's right.
But before I go on to that term, I just wanted to say that middle factor is about 1.5%. So 1.5% of the stars, on average, will host an Earth-like planet. And the star formation rate, what are typical star formation rates? In our own galaxy, it's about a solar mass of stars per year. It's not exactly one star per year because the average star is not quite the mass of the sun, but basically very similar. And so that means our own galaxy is creating about 1.5-ish Earth-like planets per century.
That's really interesting. So with the star formation rate of stars, sun-like stars, you said about one per year in our galaxy?
About one per year.
Wow. Okay.
Well, so about one star per year, and a fraction of those are sun-like stars.
Oh, I see. Okay. So
about a sixth of those.
Okay.
A sixth of the mass is in sun-like stars.
Okay. All right. So I'm sorry. Go ahead.
Yeah.
I mean,
okay.
So people need to understand this is a rate, right? So it doesn't mean really literally one star per year. Sometimes a bunch of stars form, and then sometimes no stars form. So, I mean, we've talked about star clusters and the distribution of masses, that there are a few very massive ones, and then there's lots about, like, the sun, and there are many smaller. So it's a rate. So people need to think about a rate. It's not exactly, oh, where is the one star that formed this year?
Yeah, exactly. It takes stars much longer than 1 year to actually form.
Right.
I gotta audit that, right?
On average, if you average enough million years, it's on average and sun's worth of mass is right.
Okay.
So they're not queued up.
So if I got this right, that first term is about, so one per year, you said about 1/6 of those stars are sun-like, so you got 0.16666, whatever it is, right? That's that first term.
Yeah.
Am I on there? Okay, and then this other...
Yeah, so the 1.5% actually includes the fact that not all stars are hospitable for life.
Okay, so these numbers are pretty low.
And that 1.5%, determining that number is one of the big results. That's one of the major things that has come out of the Kepler Space Telescope.
Ah, right. Good, because what I was going after we got done with this slide was, how do you know all this? Okay. All right, good.
That's not us. That's The Kepler mission.
That's how it's been an important. A lot of things have changed since Kepler's been launched, and it's good that we're getting this kind of information from it. So,
and star formation rates, right, are observational results as well. I mean, people have been interested in that for a long time, even before Hubble. I know.
Well, that goes back to what I was saying earlier.
There was anything before Hubble, but there was, and people studied star formation.
Well, that's what goes back to what I was saying earlier about the number of models. Before we had these data and observations, everybody had a model about what was going on in the world. It wasn't until we needed these observations and observations like Kepler and Hubble to tell us, well, wait a minute, your model's way wrong because we don't see anything like that. This one, on the other hand, is supported by what we're seeing through telescopes. So that's sort of what we're doing. You guys are starting. It sounds like, with the luxury of having some of this data and making some pretty good starting points.
That really cuts down on the number of assumptions we have to make. So the key assumption here is that the planet formation rate in other galaxies is similar to the planet formation process in the Milky Way, so that if you form a star in another galaxy, the likelihood of it having a planet is the same. Right, and so let's move on to the last term, the golden part.
The amount of gold in the bank,
so that's just to say, that's right. Yeah, so I guess we have a question. Should we answer the question, or should we?
No, go ahead.
Well, I'm just queuing them up for you. Don't worry about it.
Great.
Yeah.
Okay, let's finish this thought and then look at the question.
Adam, we see your question, and we will get to it.
All right, so the effect of metals is just to say that, well, just very basically, the Earth is made up of what astronomers call metals. And what astronomers call metals is any element that's heavier than hydrogen and helium. So, of course, as a star burns, transforming hydrogen into helium, and if it's a large enough star, helium into heavier elements, astronomers call all of those metals. And when the star explodes, if it's massive enough, then it releases those elements all over the rest of the galaxy that it's in. And
right,
why those are... Yeah, go ahead.
Well, I'm just going to say, so that's kind of what we learned from Carl Sagan, right? We are star stuff. So if we want, to have these rocky planets of which, these elements are made from, they got to have to first be synthesized or sort of simmered through the life cycles of stars. So that's what you're talking about here.
Yeah, that's right. So for Earth-like planets, perhaps counterintuitively, above a certain threshold for the metallicity, and that just means what fraction of the gas that's forming a new star is made up of these heavier elements, metals. There's a threshold for the metallicity, which is about 1/30th of what's in the sun, to be able to make Earth-like planets. But beyond that, the amount of metals doesn't seem to affect the number of Earth-like planets. And so
okay, wait, let me make sure I understand that. A star with metals, anything up to about 1/30th of would you say 1/30th of the amount of material in that star needs to be metals?
No, so let me say that one more time. So there's a certain fraction of metals in the sun, which is a tiny fraction. And Molly can say the number probably off the top of her head.
About 2%.
2%. Our sun has 2%.
Defined by mass is stuff that's neither hydrogen or helium.
Okay.
Right. And so stars with less than about 1/30th of that number, so just to round things completely off, stars with less than about 0.1% of their mass as metals are expected not to have Earth-like planets.
So the sun is way above that.
Exactly. But above that, how much metals, what's the metallicity you have doesn't seem to matter for the number of Earth-like planets you get. And so
and again, this is based on observations that you've gotten from
Kepler.
Okay.
Right.
Oh, let me understand. What are you saying? It's like a threshold?
That's right.
So it's not proportional. It's a threshold. You either at some level you have enough metals, and then
exactly. So the Earth is made of metals, so it's a little bit counterintuitive, right? So you'd expect the more metals you have, the more planets, Earth-like planets you form. But actually, no, because the more metals you have, that determines how the gas collapses in the planetary disks. And so actually, the more metals you have, then the larger the gas clouds that collapse. And so you actually get more giant planets if you have more metals but you don't get more Earth-like planets.
Oh, that's really interesting. I didn't know that.
Even though the giant planets, their actual composition is going to be very similar to the stars that they're around.
Right.
Okay. All right. Well, I want to. So we've got a good idea here of what you were. These were your starting points. This is how you started your study. These were the factors that you found most important: the star formation rate, this fraction of stars and planets, followed by the effect of metals, how much metals a star had, anything over hydrogen and helium.
Right.
So let's fast forward to what. So you ran was this a crank you turned and then out came some numbers?
Pretty much
Okay.
out came some numbers. So let's get to the next slide.
Okay.
Which are some numbers.
Okay. So.
Okay, but wait, I have a question. Sorry, Tony.
Oh, sure.
Oh, okay,
So
Carol, go ahead.
you talked about.
Hold on, Carol has a question.
Carol, let's just stop the hangout.
Yeah. So you talked about all the stuff that you think you have data for. Are there a couple of things that you don't have data for? I mean, you said we know this, this, and this, and we turn a crank. Yeah. So there must be some unknowns.
Yeah. So there are lots of unknowns here, actually, and so
you don't have to list them all.
Right,
I just want to get to that eventually.
Yeah. So we.
Problems with this method.
Yeah.
Okay.
Right.
I will say that one that we have glossed over is this threshold this low metallicity threshold has been hypothesized, but there's so few stars near us, and there's so few stars, for example, in the Kepler field that have that low amount of metals to begin with, that the statistics in that regime are not as robust as for stars with more metals.
Right.
Okay.
Right.
Okay, good. So, all right, Peter, go ahead, and so we've got the results up here. What's the answer?
Right. So what are we looking at here? So this is a plot, of course, and on one axis you can see the size of the galaxy in terms of solar masses.
I don't know if it's cut off for everybody else, but the bottom label, X label's cut off. It says time S. What is it? Time what?
Time since the Big Bang.
Okay, thank you. I just couldn't read it.
Yeah, so it's a linear scale, and so the left hand of the plot is the Big Bang, basically, and the right-hand side is today. And the middle is halfway through the age of the universe.
Okay, got it.
And so all this is showing is the color is telling you, as a function of the galaxy size and the time since the Big Bang, how many Earth-like planets is the galaxy forming per year. And the white dashed line is showing you the growth history of Milky Way galaxy, our own galaxy, so you can see if you follow the color under that dashed line, you can see that there's a peak in its Earth-like planet formation history, which occurred about, I would say, 7-8-ish billion years ago. That's, I guess, a little bit before the halfway point.
Right.
And also you can see this threshold, this metallicity threshold of 1/30th of solar. That's the dashed dotted line, where galaxies on average would have had less than that metallicity. Yeah. So just two key things to note about this plot. First thing is, when the universe was a lot younger, it was forming stars at a much higher rate in most galaxies, and therefore a lot more Earth-like planets were probably formed per galaxy per year.
PFR, what's that?
So that's planet formation rate.
Okay,
so that's Earth-like planets formed per galaxy per year.
Okay, good. So a whole bunch early on, about a billion years.
That's right.
Okay.
That's right. And so now at the present day, the rate has dropped off significantly. So whereas galaxies at about the Milky Way were forming, say, a dozen planets per year, closer to the beginning of the universe, right now it's much less, and so that's like 1-ish per century that the Milky Way is forming planets right now.
So if I look at this plot, I'm thinking I'm getting kind of depressed because it looks to me like all the Earth-like planets are done. They've done their.
So actually,
Tony needs a hug. He's getting kind of depressed.
Oh gosh.
Don't bum me out. No. Okay.
So this is actually a dangerous thing, because a lot of astronomers have put out news stories where they've looked at the star formation rate of the universe, and said, wow, it's declined a whole bunch since, say, 10 billion years ago, and it must be ending soon. But we'll get to that, and actually why that's not the correct story in just a bit. I just want to flash up quickly. I guess let's skip the next slide for now because we're actually getting towards the halfway point, and go to the slide number 5. Just a number.
Okay, so that's the answer.
Right. So in our own galaxy,
1 billion.
there are about 1 billion Earth-like planets. And so, as I said before, that includes things like Venus and Mars, but of course it includes Earth as well. So there's a fantastically large number of planets.
This is the whole universe.
No, this is just in our own galaxy.
Our galaxy.
Okay, 1 billion in our galaxy.
If you go to the next slide, then that's the number of in the Hubble volume. Or
I like your pictures at the
digits.
bottom. Earth,
Yeah.
and then you have Sloan digital skies.
Right, exactly. Exactly.
It was
Okay.
1 in a million, now a billion, and now it's 1 in a lot.
Okay, yes.
Lots.
So it's.
So what's that number, Peter?
If I verbalize it, it's 100 million trillion Earth-like
100
planets.
million trillion. That's a gajillion for those of you who are
Okay.
tuning in. A gajillion. Okay.
Which is a lot, right?
Yeah.
Yeah.
This is up to now.
Yeah.
Okay, so up in the history of
So
the universe.
no need to be depressed.
Okay,
So-
I'm not as
so
bummed
no-
as I
no need
was
to be
moments ago.
depressed.
Thank
But
you.
But then actually there's something cool, which is about the future. So as you saw earlier, the star formation rate is declining, of course, in the universe. But it's actually fairly dangerous to extrapolate that it'll continue to decline forever and just stop at some point. Because the next slide shows the composition of the universe in terms of what are the materials available to form stars. Okay, so adding up to 100%, of course, you have things like dark energy and dark matter, which we're still searching for. What are those things exactly? Is there a particle that corresponds to dark matter? What actually is dark energy? But if you look at the more familiar elements, so that is hydrogen and helium and stars and remnants and so on.
Yeah, that's the famous 5% of the stuff that we can see,
Exactly.
smell, touch, feel, interact
Exactly.
with directly,
So
right?
This is the thing that can depress you or make you very angry.
Yeah, that 95% of the universe,
I know,
90,
we don't
won't have
even
anything
know
to
what
do
the
with
hell's
us.
going on.
I know.
Right.
It won't even
Yeah,
have anything to do
whatever.
with us at all. I know this.
Still gotta have therapy tomorrow.
Let's talk about heat death next. No, okay. Well, yeah.
Right.
So actually, I want to ask Molly before we go too far along, Peter. Let me just ask Molly where we are up to this point. This gajillion of Earth-like planets, these planets that have already been formed. Was this stuff that you were pretty comfortable with when you started? I mean, I know that your study extrapolates into the future, and I'm gonna let Peter continue on that. But I want to get your comments so far on this whole thing. Was this something that was a surprise to you that there were this many Earth-like planets already?
So I think that those raw numbers weren't surprises at all, because as the Kepler data were coming in saying, look, most stars have planets, the idea that, well, there are a hell of a lot of stars in the universe, and therefore there are probably a lot of planets, wasn't a very far leap. And so a lot of these numbers are representing the fact that, the Milky Way has a lot of stars in it, and the universe has a lot of stars in it. The new interesting part of this is tying it to the rate at which the planets were formed in the past. And therefore we can start putting the Earth and the solar system in context for, our solar system has been around for 4.6 billion years. Does that mean that we're young? Does that mean that we're old as we're looking around at all of the other planets and therefore potential civilizations in the Milky Way, or in the rest of the universe? We can start actually now saying where we fit in cosmically with the other planets that are out there.
Well,
That's
right.
why
Scott,
very interesting.
maybe it's a good time to look at slide number 4.
Conclusions.
Right, and if you look at that, and according to that peak of planet formation that Peter showed us earlier of about 6-7 billion years ago, it would definitely tell us that we're pretty young compared to some of these.
Well, so that's another, it's tricky because just because something was forming at the fastest rate back then doesn't mean that's when the most number total was formed.
I don't get it. How come?
Which is what this plot that Scott just put up. Do you want to explain this, Peter, or do you want me to?
Yeah, so all that Molly was just saying is that if you're going 100 miles per hour, but you only maintain that speed for 1 second, and the rest of the time you're traveling at 2 miles an hour, then the greatest distance you travel is actually going to be covered when you're traveling at 2 miles an hour and not that 100 miles an hour for a very short time. And so that's what's going on here. That's what's going on here is that, again, the bottom axis is probably cut off, but the left-hand side is Big Bang, basically the right-hand side is now. It's a linear scale, and then how many planets have been formed in the Milky Way? And so Earth-like planets are this black line. The halfway point is the blue square, which is almost the halfway point for the universe. And then the dotted line vertically is when did the solar system form. So for Earth-like planets, we actually came a little bit late if you look at only the things that came before the present time. So the Earth formed 4.6 billion years ago, which was about after 80% of the currently existing planets in the Milky Way formed.
So that black line is the total number of planets that actually form, not a rate.
That's right.
And Earth-like planets.
Earth-like planets. So, and where the dotted line is where we are. And as you point, so what you're saying, if I get your analogy, just because there was a whole lot of them forming early on, in other words, that was that red part of your previous graph, doesn't mean that that's when the most of them were formed, right? Am I understanding your analogy?
Yeah.
Okay, so here we're at this point where we still got more planets to be where we formed. There's still a lot more that formed after us, so we're not necessarily late to the party.
Yeah.
Okay. All right.
The other interesting thing to think about here is, right, so the Earth, the solar system formed right at the average, median, typical time for solar systems to form that have giant planets like Jupiter. And there are a lot of theories that say, well, for whatever reason, you need to have a giant planet in the solar system in order to keep out, things from the Kuiper belt or further out from bombarding the inner Earth-like planet. Right? If you have too many asteroids hitting the planet, too many mass extinctions, you're not going to form a civilization. So you might expect for civilizations to form on planets that exist in solar systems with giant planets.
Okay. I want to go back to the bit about the matter in the universe and the stuff that all the stuff that we were made from, and the stuff that was left over after a lot of this star formation. You already talked about metallicities. We talked about stars forming, and you were about to make a point going toward the future. We've talked about all of this as the way it's been up to now. What can we expect going forward? So why don't you pick it up there?
Sure. So if we take a look at just the matter that is familiar to us, the 5%.
Right, we've seen this, this pie chart's very familiar to a lot of us,
right. So about half of that is not bound currently, but about half that, so 2.5% or so, is bound to gravitationally collapsed objects. And so that means
whoa. So 5% of the, you're already at the 5% level of all the stuff in the universe, and only half of that, roughly, is bound to something. The rest is just floating around in the universe?
So, right, so you have gas in between galaxies.
Now he's getting depressed.
Yeah.
Okay.
So
well, no, not necessarily.
I'm going to call out to Twitter to give you a Hubble hug. So cheer up.
Oh, I need a Hubble hug from the Hubble huggers.
We'll do a hangout someday on intergalactic space, and that'll really the brain.
Okay, so so of the stuff that's bound, obviously that's the stuff that can make the planets. And you went forward and found that, well, what was? Go ahead and give us a punchline, because I want to get to some other stuff here.
So the punchline is there's 2.5% of the matter in the universe, or energy budget of the universe, which is stuff available to form stars. And of that material, only 10% has currently turned into stars as we speak.
Of the stuff that's gravitationally bound.
Exactly. And so,
I'll be damned.
Of that material which is available to form
it's hard to
stars.
form planets if it's not gravitationally bound.
Well, that's why I just wanted to clarify. Yes.
That's exactly.
I'm still bummed about the stuff floating out there.
I know.
That matters. It's like when you ask a short person that's like 5 foot, they say they're 5'2.5". That little half really matters to them, right? Well, it's like, it's the same thing here. That little half really matters to me.
That's right.
I'm 6'1/4 inch. All right, it matters to me too.
Thanks for ruining my analogy, Scott.
Right. Okay, yeah, so the key point is, of the material available to form stars, let's just go to the next page, or next slide.
Yeah, let's get off this one.
Right. So only 10% of the material available to form stars has actually done so. And that means in the remaining future of the universe, the remaining 90% will, at some point, eventually turn into a star or a planet.
See, that's my hug. I feel really good. So 90% of the stuff is ahead of us. This is
right. So it's
But
again
you'll
like
never be around to see it, Tony. So
that's right.
No,
I don't need to be. I just need to know it's there. See, I don't need to be. The universe isn't all about me. Mostly about me.
Just a deep field.
Yeah, just a deep field.
Just a deep field.
So only 10% of all Earth-like planets in the 13 and so billion years of the universe have actually formed yet.
That's right.
Wow.
And so even though the star formation rate is decreasing, and it's decreasing for good reasons, which it would be too long probably to talk about right now, it'll eventually reach a sort of lower floor and continue. The universe will continue forming stars for a very long time, perhaps.
And that's the 2-mile-per-hour part of your analogy, right? We may not be forming as many, but we're plugging along, and we've got the history of the universe, especially since we're accelerating, to do this. And so overall, we've still got most of the planets ahead of us.
Yeah. And to use one of Molly's favorite terms, we'll be forming stars for at least a tera-year. Not a year, a tera-year.
Tera-year. Oh, wow. That is a great word, actually.
I think this is just a thinly veiled argument for telescopes long into the future.
Yeah, we need more observations.
Is there anything that we could not in our telescopes?
I know. It's like endless supply of telescopes required.
Right.
Ever bigger.
Okay, so you've given us good foundation for why this has happened, and the number of planets that we think have formed already in the universe, only 10% Earth-like planets. Okay, so in our galaxy, there's 1 billion Earth-like planets right now.
Right.
That's what you said, roughly.
Right.
And so we can expect more in our galaxy in the future.
Yeah.
On more of this 2-mile-an-hour rate. We're plugging along. We're going to make it. Now I'm going to ask you to speculate a little bit, because I want to know about life.
Oh, really? Oh, really? Now speculate?
What do you mean? We've been doing science right now. It's based on. What are you doing?
Okay,
It's based.
Mute.
They base this on observations, and well, let's before we go to that, the speculation. How confident are you guys? I've comment on that. Of your numbers. Let's talk about you know why you started, as you pointed out, Peter, with you've been able to minimize your assumptions based on actual data from Kepler and Hubble and others. How confident are you in these results? What are the error bars? And I'll have Molly comment on that too.
Yeah, so the biggest question actually is with this future stuff, and it's whether the gas will stick around to be available to make stars. Because
so the stuff that we know up to this point, the 10% or the 10% number, you're pretty confident about that.
Yeah. So the fraction of available material that's been turned into stars being 10%, that we're very confident about. And the question is whether that material will stick around in the future to make stars. And from what we know, based on Hubble observations of gas around galaxies, such as the Cos Halos project that Molly's been a big part of, not escape to become unbound, where it would not be available to form planets in the future. And that's one of the key things that gives us confidence in the fact that that gas will eventually form stars and planets of its own.
Okay, all right. And Molly, you want to comment a little bit on this?
Yeah, so I think the biggest uncertainty is I mean, we're pretty sure that the gas that's currently outside of galaxies, that's not yet formed stars, gravity is pretty difficult to resist, is going to eventually gravitationally collapse and form stars. The part that's less certain is whether or not the environment that those stars are going to be forming in, tens of trillions of years from now, will be similar enough to the environments that the stars observed by Kepler were formed in, and whether or not that rate of planet incidence that we've assumed will actually hold throughout the entire future of the universe.
That's a good point, because the Milky Way is in a certain stage in its life cycle, which we've, the universe now, the Milky Way now will be quite a bit different than the Milky Way.
So, for example, one of the things we consider in the paper is, do you get a different incidence of planets if the stars are forming in very dense clusters that you might expect to have in the very far future when everything's more gravitationally collapsed into one big super galaxy or something like that. And as far as the observations have, that for close-in planets like the Earth, the incidence isn't that different around in those different environments. But that is one worry that we had.
Okay. All right. I'm getting a lot of questions. I want to make sure I get to as many of them as possible, so I want to keep this next part really brief. Everybody, well, not everybody, but a lot of people who watch our Hangouts know about Enrico Fermi and his famous question, where is everybody? And the basic hypothesis is the galaxy is old enough, there are enough stars, and now we know enough planets in the universe where there's plenty of time for an alien civilization of some kind to have been born on those planets and lived out their lives, and we should have seen them by now. So the famous question is, where is everybody? It got the name the Fermi's paradox. And I guess when I listen to you guys talk about this, what goes through my mind is that, you know what, the game's not over yet. In fact, the game has hardly even started. If only 10% of the Earth-like planets have formed, and that's where we expect most of life to probably have come from, or at least we have every reason to think that's a reasonable assumption to make, then we really have a lot to look forward to, perhaps, right? And could you guys comment very briefly on that?
There are two kind of different ways to look at it, right? So either you can look at these results and be like, oh my God, there's so many planets. The solar system formed at a typical time for planets in the Milky Way, but it's taken us 4.5 billion years to get a spacefaring civilization. So maybe the older planets out there, by the time they got around to making a spacefaring civilization, they managed to kill themselves off very quickly, something like that. Look at how long it took for us to go from the Wright flyer to the atomic bomb. That's the depressing way of looking at it. I think the really exciting way
I'd say so. Yeah, that's pretty
depressing, right? I think the exciting way to look at it is, we've all seen, science fiction shows or read science fiction books of where there's the ancient alien race that's been around forever. Maybe that's us.
All right. Maybe. All right. Good.
No, you need to do your best aliens pose.
All right, Peter, do you have any comment on that? Then I'm going to get to some questions.
Yeah, well, I think the Fermi paradox is still pretty much unchanged, because what we're predicting is the future. So most planets, and we expect also civilizations, will arise in the future, but that doesn't change how many planets exist right now in the Milky Way.
Right. That says something, but the 10% figure means there's not as many as there could be, and so
not as many as there could be, but there's still a billion planets out there.
Right. Okay. Point well taken. I'm doubting
it. If life is common, then where are they?
Exactly. It's still a valid question. This isn't. But I would say, based on what you've done, we've got a brighter future than we may have right now. So that's cool. Right. All right, let me get to a couple. Yeah. I just want to get to a few of these questions before we run out of time. John Glasgow on the Q&A app is asking, is Peter's slideshow available, or will it be available, maybe with a brief explanation that non-astronomers can understand? John, we're doing it right now. If you don't understand, we're failing. No, this is all you're going to get. I suppose we could post it somewhere, but I think this is the kind of explanation. We just use those slides as kind of a backdrop for the discussion that we're going to have I don't know if we can make it available somewhere, but maybe. But I doubt it. But we're trying to explain it to you as best we can right now, and I hope this is helping. So if you want to, if you have further questions, go ahead and ask them now. Why don't you go ahead and read, Scott, to us the question you had earlier from who was it? Adam Synergy. Thank you.
Yes. So Adam asked on actually the Google event, might we expect planets in the far future to be subject to a greater amount of radiogenic heating from larger concentrations of available heavy elements in their cores created by an ever-increasing number of supernovae? I did warn you about some really good questions.
Yeah, radiogenic
Wow.
heating.
Yeah.
Wow. That's awesome.
Right?
Can I answer this one?
Sure, go ahead, Molly.
Go for it.
I'm gonna say no. Because so the Earth, right, is basically 100%, and so future, even after many more generations of supernovae, you really can't create a planet that has, that much more heavy elements than the Earth already has. The stars that the planets will be around might have higher amounts of metals in them, but that'll actually decrease the amount of violent radiation that those have. Stars with more heavy elements in their atmospheres have less radiation in the ultraviolet, so I don't think it's something future civilization that'll hamper the development of future civilization.
Okay, what's radiogenic heating?
Yeah.
Yeah, Molly.
So,
You know what that is?
I rolled out the first half of the question, didn't have to care about the second half.
okay, so if I could just chime in,
Sure.
I think Molly's explanation is absolutely
Yes.
right here, and it's not. Are there more elements in the future? But really, does the proportion of radioactive elements change in the composition of the planet?
Right.
And as long as we have the same stars exploding, or the same distribution of stellar masses exploding, which you do, then the composition doesn't change, and so you expect the same fraction of radioactive materials, which give you the same amount of radiogenic heating.
I see. Okay, thank you. Thanks for the clarification. So, all right. So we have a question on Twitter, Scott, from Fine Woman. You want to read that one?
Yeah, let me go and pull this up here, and I actually have another one I want to put up too. But let's
Okay, go ahead.
with that.
Okay.
So I still love your Twitter handle, Julia.
Yeah, I agree.
Feynman. A bit confused on the PFR plot and metal threshold. Is 1/30th a dynamic number whose value was lower for a younger universe?
The answer is no. Just 1/30th of the sun's current metallicity is the theoretical threshold for Earth-like planet formation. And so that's a fixed number, which is about 0.1% by mass.
Can you put that plot back up, Scott?
So, I mean, related to a little bit of Adam Synergy's question, so you have this threshold effect where you need, it's sort of like saying, well, you need a minimum amount of metallicity. One of the questions is, do we know anything about, like, quenching of star formation at high metallicity? I guess we don't, because we don't have any limits, or do we?
Hold on. So I just want to explain again what this dash line is. So what this is showing, so galaxies on average have some average amount of metals, number of iron atoms per hydrogen on average. And that metallicity, that number changes both with how massive the galaxy is and with how old the galaxy is. So galaxies way back in the day, before as many supernovae had gone off, had less iron. And smaller galaxies also tend to have fewer supernovae go out per, as the amount of gas that they have, so they also have lower metallicities. So the reason why this line looks like looks like a curve and has the shape that it does is it's tracing, on average, what is the galaxy mass as a function of time that has this threshold of metallicity.
Okay.
So it's just indicating that if you're a galaxy that's below that line, then you won't have enough iron in order to actually form Earth-like planets at that time, on average. Basically.
Okay, good,
Yeah.
good. Thank you.
That's
All right,
just
so
what that line is.
so Ian Harris has a comment here on the Q&A. Maybe we shouldn't forget about the moons of these exoplanets while looking for life, etc. You're right, and we didn't even talk about that. That wasn't even something we were going to talk about much. But of course, there's moons around, especially gas giants and other kinds of planets in the universe where we could be talking about life. But of course, here we're talking about the possibility of forming Earth-like planets or sized planets. So that's a good point. Thank you, Ian.
But if Kepler gives us data, we'll just crunch that through the machinery. If you give
that's
us
right. Okay.
incidence of moons around giant planets.
Yeah. Okay, Scott. So I'm seeing some comments here. We've read some of them. Astro Girl 1 USA is like Molly answered her question, so that was good. Thank you. And here's one from Astro Girl. Are all gas? This is one maybe she answered. Are all gas giant planets gas? Are all giant planets gas, or can giant planets be rocky? And I think you covered that with some of the definitions early on, correct? Of what the size of an Earth-like planet. Okay.
So that's actually
Observationally, as far as what you can do with the Kepler data, by looking at the transit of a planet as it goes in front of its host star, is you can get a really good handle on both the size, the radius of a planet, and its mass. And by dividing those, right, you can get the density. And so you can say, well, is this more like the density of air, or is this more like the density of a giant solid block of iron? And basically the densities that they're finding for what we're calling giant planets tend to be more like the densities of Jupiter, much, much, much lower densities than something like Earth or Mars or Venus.
Okay, good. Good question. Thanks for asking that. So, Scott, is there anything more on Twitter you want to bring up?
I have one more thing from Twitter I want to bring up, and this is actually specifically for you, Tony. But this is for Tony Needs a Hug. This is from Pillownet, from Heather Archuleta, and you stop doing math.
That is so wise. Thank you. Thank you. Yes, I should not be doing math, because math. You know what I tend to do when I do math is I divide by 0 a lot, and
you know. That's why so many things about you is undefined.
I know. Good one. Okay. Great.
Thank you.
All right. Okay. So let's talk about the future of this research. So, in the future of our universe, what about the future of this work that you two are doing? Are there plans for more of this kind of work? And Peter, I'll start with you, and then Molly, I'd like you to comment.
Yeah. Well, seeing planets in other galaxies is going to take a lot of work. But one of the things which we're very excited about, of course, at Space Telescope is the high-definition Space Telescope, which we expect will be able to detect signatures of life around other planets.
See, what are we doing?
Yeah. The reach of that will actually be very competitive, if not better than what SETI is able to do now. So I don't know, Molly, if you want to comment a little bit more on that.
Yeah, so this is the High Definition Space Telescope is a current concept for a space telescope to be launched in about 20 years. That the primary driver for this is what do we need to do in order to robustly detect statistically the occurrence of biosignatures on Earth-like planets around Sun-like stars. Full stop.
Cool.
And so basically that was the question that they went out and found. It's not like we want to find biosignatures on maybe one Earth-like planet. It's like, no, we want to know statistically what fraction of Earth-like planets around Sun-like stars have biosignatures. So this would be like chlorophyll or the ratio of oxygen to O2 to ozone to CO2 in the atmosphere, that there's no way to have that happen in equilibrium, and you have to therefore have life actually producing O2 like we do on Earth, things like that. And the concept is for a 12-meter diameter telescope in space. So for comparison, Hubble is 2.4 meters, so be about 5 times bigger than the size of Hubble. And the amazing part is if you have that question as your science driver, it's going to boost the rest of astrophysics so extraordinarily, and also help us understand much better, how do stars form in detail 10, 12 billion years ago. Right now, our pictures of galaxies from Hubble are very fuzzy. They're incredible compared to what we had before the installation of the new cameras in 2009, but they're still much fuzzier than our pictures of local galaxies. But if we can get that resolution at higher redshift, and when the universe was much younger, we'll actually be able to tie these questions together much better of where did we come from? How does this whole story fit together?
Awesome. So I'm going to have to stop us there. HDST is in the future. JWST will be looking mostly at planets within our galaxy. HDST much further away, much bigger telescope. Looking forward to that a lot. So I want to thank everybody for doing it. I'm going to have to stop us here. Join us next week. We'll be back next Thursday. We're working on it. Carol, do we have a topic yet, or are we still...
We're going to have some repeats from, remember the guys who were doing the galaxy stuff? I think it's going to be the 21 centimeter workshop.
Oh, that's right. Okay,
about
good.
Cosmology and that stuff. So
space.
All right.
Tune in next week for space.
More space, right?
Stuff. More
As
space
Hubble,
stuff.
Hubble space
It'll
stuff.
be
All
more
right.
space stuff.
Well, thank you very much on behalf of Peter Beruzzi, Molly Peoples, Scott, and Carol Christian. I want to thank you all for watching, and we'll see you next week.
You.
Follow us on at Hubble Telescope. I'll be around next week with another Periscope right beforehand. Thank you all for watching, and as always,
keep looking up.
Looking up.
Hello, everybody, and welcome to this week's Hubble Hangout. My name is Tony Darnell, and you have found yourself in one of the few places, if not the only place, where you can get direct access to the latest science and discoveries from the Hubble Space Telescope, along with an opportunity to directly interact with the astronomers who use Hubble every day to try and understand the universe and our place in it. So this week, we'll be talking with astronomers from the Space Telescope Science Institute, whose latest research suggests that most of the Earth-like planets in the universe have yet to be born. I mean, that right there just blew me. That caught my attention right away. We'll talk about that and the implications for this for exoplanet research and what it might say about Fermi's famous question, where is everybody? And we'll get to them in just a minute, but before I get started, let me introduce my colleagues, Dr. Carol Christian. She's the HST Outreach Scientist. Hi, Carol, and welcome. It's good to see you again.
Hello.
Missed you last week.
You. Yeah.
You were traveling. That's right.
I was in Jerusalem. That was fun. Anyway,
So this year in Jerusalem. Okay. Also with me, joining me is Scott Lewis. He's monitoring our internet channels and also helping with the discussion. Hi, Scott. It's good to see you again.
Yes, good to see you too, Tony.
Cool. All right. Well, before we get to our hangout and I introduce my guests, I want to do one announcement that I found out over the past few days. Thanks, Scott. That's good. That's a good point. Okay, so let's get to this week's hangout. Astronomers at the Space Telescope Science Institute. Turns out we do more than just look at Hubble data. There's also theoreticians in the house. Now, I don't know if either of these guys would consider themselves theoreticians exclusively, but we'll talk, and I'll ask them about this in just a minute. But joining me is Dr. Peter Beruzzi. He's an astronomer and postdoc at the Space Telescope Science Institute. He's joining us all the way from Japan, and so he is woke. So he says it's 4 in the morning there. I want to thank you, Peter. Welcome to our hangout.
Thank you. It's great to be here.
Yes, and because of the time delay or the time difference, we'll be getting audio from him throughout the hangout. So, but at least we have him, and that's great news. He's the lead author of the paper that appeared on the October 20th monthly notices of the Royal Astronomical Society, and also on that paper is Dr. Molly Peoples. She's been in our hangouts before. Hi, Molly. It's good to see you again.
Hey, Tony.
Now you're actually at the institute, so
I am at the institute.
Yeah, and so she joins us. She was also on the paper. Let me get this is Exoplanet Week. I know this. because the hashtag is all over Twitter, right? This is
Yeah.
We're trending.
That must be true. Yeah, absolutely.
so it's on Twitter, so it's got to be true. And NASA Goddard and all these, a lot of there was a Ask Me Anything on Reddit about exoplanets that Goddard held, and it happened. It was about 2 o'clock, so it's over now, but which totals about 57 meters per second. So that was what their tweet said earlier today, and so they're getting ready for all of that now. And as I said, Hubble had a role in this. We helped them identify some potential targets, 3 potential candidates. If you want to learn more about them, you can go to the link to the planetary.org blog from that Emily wrote last week. So just wanted to say that. Also, Astronomy Night happened last week, or Monday. Did anybody happen to see what was going on with that? No? I didn't get to go. We didn't get to go.
I just got up to San Francisco. So
I know. I saw your tweets. There. I saw you doing a road trip on the way to San Francisco. So.
Well,
anyway,
apparently, there was the usual got to get your telescope in, security, all that kind of stuff. But they said it was a very successful night. This year, I don't think the president wandered around so much. He came out and made a speech, yay verily, and then people looked at the moon this year instead of a binary star. Apparently, for some reason, they chose a binary star last year, which I have no idea why people would want to look at that. But anyway, they looked at the moon. They were much happier.
I didn't even think about it. Cool. I'll bet more than one Secret Service agent had a bee in their bonnet over trying to get telescopes on the south lawn of the White House.
Oh, yeah. So apparently last year they had to send them in like a day in advance and all that. And this time they loaded all their stuff in the NASA.
NASA's New Horizons spacecraft, I'm sure you guys remember that, flew by Pluto last July and looked at things and sort of changed our view of that outstanding system of bodies out in the outer solar system. And there's a next stage to the mission, which I think is yet to be funded. I don't think they've gotten funded to complete this part yet, but they need to start thinking about it now. And I was reading Emily Lakdawalla's blog last week where she was talking about that they finally have a second target for New Horizons to fly by. Now, I put the link to all of this in the description box, so you can read more about it there. But it turns out that Hubble actually gave New Horizons some potential candidate Kuiper Belt objects to go to, and they are very imaginatively named PT1, 2, and 3. PT for potential target. Now, I think the favorite, according to what Emily has written and what I've read on the Twitter feed from New Horizons, is that PT1 is going to be the most likely one they go to. And so, but they have to kind of get ready now, right? Because, physics, they have to fire the rockets and get the spacecraft positioned such that it can make the flyby in a reasonable amount of time. So they're working on that now. And from what I've seen on the Twitter feed, is that the burn is going to be, what did they say here? It was like it's going to take 4 engine burns over 2 weeks.
The truck, and they went over. It was still a hoo-ha, but they got stuff in there.
Yeah, good. Well, NASA Horizons got a shout out from the president, and a lot of people excited about the work they're doing. So the story is not over with New Horizons, folks. It's hopefully, I don't know when we're going to get word on the funding for the next stage of that project, but certainly data are still coming down, and they're still analyzing it now. We're hearing new things about Pluto almost every, exactly.
Yeah, very nice data, and we did help them out by scheduling some observations to see if we could find one of these Kuiper Belt objects for them, and so we accumulated some data for them, and they analyzed it, and they found, as you said, 3 objects, and they picked one. So.
Yeah, and Emily's got a real nice chart on her blog post about the characteristics of each one of the potential targets, how big they are, and all of that, and when it might encounter it. The first one, PT1, is in January 2019, so we got some time before it gets there. But like I said, they have to plan ahead and get the thing pointed, or at least on the right trajectory now, so that when it makes the flyby, that will
be just in general, I mean, Emily's blog is fantastic. So
Agreed.
Following Emily Lakdawalla, I don't know how she gets out as much work that she does all the time, and I've worked beside her, and she's just amazing. So follow her blog, and her Twitter account is fantastic too.
Yeah, she's a huge source of information for me on Twitter as well. I agree. Yeah.